In the last lecture, we had looked at two-port networks and the equivalent circuits, Z parameter, Y parameter, and H parameter equivalent circuits. These were equivalent circuits to a black box from which two terminals were sticking out, and just to remind you, we were using Taylor's theorem for multiple variables to first order in such situations. So within the framework of this approximation, these are all equivalents to the same circuit. So obviously, two different two-port equivalent networks must themselves be equivalent to each other. So, for example, we should be able to figure out the H parameter equivalence of a circuit if I were to know its Z parameter equivalence, and vice versa. Of course, the same can be said about Z parameter and Y parameter and H parameter, and so on. So, in what follows, we are going to take a quick look at how to derive the H parameter equivalence of a two-port network if I knew already the Z parameter equivalence. Now, this is just an illustrative example. You could carry out a very similar analysis for the other pairs that I mentioned right now. So just to remind you, these here are the Z parameter and the H parameter equivalent networks to a circuit. So for the Z parameter equivalent, remember we take the input and the output currents, capital I and capital I-O, as the independent parameters. Here I am using the input-output notation rather than 1 and 2. There is no real mathematical difference between the two cases. And just to remind you, the two-port network theorems are in the context of small signal application. So there is a quiescent point or dormant value for each of these currents and voltages in the circuit. And what we are interested in are fluctuations from those dormant values or quiescent point values. So small ii, small io, small vi, small vo, the ones which are marked in the circuits here, are all fluctuations from the quiescent point values. And as you can see on the left hand side, you have the Z parameter equivalent. Just a quick reminder, the Z parameter equivalent circuit has this. On the input side, it has an input impedance Zi in series with a current controlled voltage source ZRIO. So it's a voltage source whose voltage is controlled by the output current. On the output side, similarly, it has an output impedance ZO in series with a current controlled voltage source ZFII, where the output voltage is controlled by the input current II. The H parameter is slightly different. On the input side, it's very similar. It has an input impedance HI in series with an input series with a controlled voltage source, but this time it's a voltage controlled voltage source HRVO. On the output side, on the other hand, it's not a series, it's a parallel combination of a current source HFII in parallel with an admittance HO. Of course, the admittance is HO, you can also think of that as a resistance of 1 by HO. And we had already derived these results before. For example, Zi is of course nothing but the input voltage Vi divided by II, provided this particular controlled voltage source is set to 0, which you can do by setting IO to 0. So what we say is Zi is the input impedance, input voltage by input current, divided under the condition of the output being open, IO equals 0. Just to remind you once again, these are all fluctuations. So what Zi really is a change in the input voltage, capital Vi, divided by the change in the input current, capital II, under the condition where the output current, capital IO, does not change. Of course, if you remember our last lecture, the formal definition of Zi from the Taylor series was, it says del Vi del II at constant IO. So this is, of course, the partial derivatives expressed in terms of small signal or small fluctuations. Let me now point out one very important issue which might be confusing to people who are seeing this for the first time. As you can see, Zi here and Hi here are both input impedances. Basically, they are input voltage by input current. Of course, fluctuation in input voltage by fluctuation in input current, but in the context of AC signal analysis, what we are doing here, we will drop the word fluctuation. It's just input voltage by input current. So both Zi and Hi are very similar, but they are not identical. Why are they not the same? Because Zi is evaluated under I/O equals 0, that is output open conditions, whereas Hi is evaluated under VO equals 0, that is output short conditions. So they are both input impedances to the same two-port network. However, they are input impedances evaluated under different conditions, and that is why they are two different quantities. So in the following, what we are going to do is we are going to take a look at how to derive the H parameters from the Z parameters, and the hint there will be just these equations. We will just use them. In particular, take a look at this. Both Hi and Hf are evaluated under output short conditions. So what we do is we start with the Z parameter equivalent network for my black box, and because I want to set the output short for calculating Hi and Hf, what we will do is we will just put a wire, or imagine that we are putting a wire here. On the other hand, I need the input current to be II, and the way to ensure that is that I will connect a current source, a constant current source whose magnitude I can control, and whatever it is I'm going to call II, and that of course drives the current II through the input side. So under these conditions, I need to calculate what Vi and Io are going to be. Vi is actually pretty straightforward. We need the value of Io first. Io here is pretty easy to see. There's only a voltage source ZF II here, and in series with an impedance ZO. So current in the circuit is of course ZF II divided by ZO, but that current, as you can see easily, is in the counterclockwise direction. Since Io is flowing in, that remember is our convention. All currents flowing into the two-port network at the upper terminal are considered positive. Io is actually negative of this current. So the only thing you have to be careful about in these calculations essentially is the sign. Io is not ZF II, the voltage, divided by ZO, the impedance. It is minus that. The minus sign comes from the direction. So that's pretty straightforward. Now that I know Io, I can plug this in here and I can immediately see, even before that, since I've got Io, in terms of II under VO equal to 0, the ratio immediately gives me HF. HF is nothing but minus ZF by ZO. HF, remember, is a forward current transfer ratio. It's a dimensionless quantity. It happens to be the ratio, apart from the negative sign, of the forward transfer impedance and the output impedance. Fine, so we have already managed to find out one hybrid parameter in terms of the Z parameters. Well, what about Vi? Vi, as you can easily see, is the sum of Zi, II, the drop across Zi, and the drop across the voltage source ZR/IO. But now that I know that IO is this, I can plug this back in here, and I get the whole thing is Zi minus ZF ZR by ZO into II. So ZR is already sitting here, and you have a minus ZF by ZO factor from here. Of course, the ratio between Vi by II is simply Hi. So as I said, Hi and Zi are not the same. They are both input impedances, but because their input impedances are under different conditions in the output, their values differ. The connection is straightforward. Hi is simply Zi minus ZF ZR by ZO. So we have managed to find both our hybrid parameters for output shorted conditions directly. The next set, HR and HO, are evaluated under input open conditions. IO has to be 0 for them. So because IO is 0, what I have done is I have connected nothing here, which means IO will automatically be 0. And now comes this important issue. How do I ensure that the voltage VO is maintained here? If there's no input, how do you get an output? The answer lies in the fact that the input-output division is really more in our minds. What we can always do is, at least in theory, can always connect a voltage source directly across the output to maintain a voltage VO across the output. So this is the important thing. And because II is 0, notice that this derive II, this controlled voltage source here, also vanishes. So it's replaced by a short. So this is our circuit. And what we need to do is find out VO and IO under these conditions. Sorry, VI and IO under these conditions. VO, of course, is something you directly control because you have put in the voltage source VO. Well, IO is straightforward. It's just VO by ZO. Right? This is just a series circuit with a single impedance ZO. So you get IO is VO by ZO. So HO, the output impedance, simply works out to be 1 over ZO, the ratio of IO and VO. Of course, the II equal to 0 condition is already maintained because of the way we connected our circuit. The final thing that we will need for HR is VI. How do you get VI? VI is the voltage here. Of course, that voltage is the sum of the voltage drop across the input impedance, which is 0 because there's no current. But there is still a voltage drop here, that's ZRIO. So VI has to be simply ZRIO. And IO being VO by ZO, I get ZR by ZO into VO. So what is HR? It's just the ratio. HR is simply VI by VO, so that's ZR by ZO. So we have managed to find out all 4 of the H parameters in terms of the 4 Z parameters. Of course, you could invert this set of equations to find out the Z parameters in terms of the H parameters. Or you could just as well start with the H parameter equivalent circuit, just the way we did here. Instead of starting from the Z parameter equivalent circuits, we could have started with the H parameter equivalent circuit, maintained the conditions for finding out the Z parameters, namely output open or input open, and done an analysis very similar to this and figured out the inverse relations. And very similarly, we can find out the relationship between the other sets of equivalent parameters. So this is how you can establish the equivalence between the different equivalent circuits, also convert from one to the other depending on whichever is convenient. And this will come in very handy later on when we start analyzing circuits, especially nonlinear small signal circuits like amplifiers in earnest. Now let's move on to the next topic today. The next topic today is a slightly advanced one, and this again is going to be used in its full glory later on in the course, but I wanted to just illustrate how you would use, say, the H parameter. I'm just using H parameter as an illustration here. You could use any one of the other equivalent circuits as well to calculate the amplification or gain in an amplifier network. Suppose there's an amplifier whose equivalent circuits I know. An amplifier is an ideal case study for a two-port network system, right? You have an input on one side, you have an output on the other. And here what we are asking ourselves is, how does the gain of an amplifier which is there in that black box in the middle, how does the gain depend on the load resistance RL? If I change the load resistance, how does the output voltage by input voltage, VO by VI, change? And we are assuming right now that somehow we know the H parameter equivalence for this amplifier. For a given amplifier circuit, how to find the H parameter equivalence? That will, of course, be a major part of our discussion when we talk about amplifiers in general. So, assuming that we know the H parameters, I can write down the equivalent circuit, the H parameter equivalent circuit here. Okay. So the black box contains the amplifier. We don't really know at this stage what exactly is going on inside the black box, but we do know from our two-port network theorems that we can replace this black box by an H parameter equivalent circuit. And I'm assuming for the timing that the four important parameters HI, HR, HF and HO are known to us. Okay, now how do we analyze this circuit? It essentially is straightforward. What we do is use simple circuit analysis. For example, what we want is to find out the output voltage VO. But look at the output circuit. On the output circuit, there's a single amplifier, a single current source, HFII, and that's driving current through this parallel combination. The parallel combination is that of an admittance HO in parallel with a resistance RL. Of course, it's simpler for us if we convert both, at least mentally, into resistances. So HO is really the resistance HO inverse, 1 by HO. So we have 1 by HO in parallel with RL. So what is the effective impedance of this parallel combination? Well, we know that it's 1 by HO into RL divided by 1 by HO plus RL. So multiply that by the current, which is HFII, I get the voltage drop across the parallel combination. Well, is this VO? Almost, except for the fact that VO has to be negative of that. Again, notice the current is being driven downwards according to our sign convention by the current source, which means the voltage drop it creates is higher on the lower side, less. So it's a drop when you go from bottom to top. But VO is a drop which you measure from top to bottom. That's the sign convention that we are using. That is why VO turns out to be negative of this voltage drop. Simply multiply the current HFII by the impedance of the combined parallel network and put in a minus sign just to get the sign of the voltage right. Once again, the directions and signs, these are what might cause some confusion. So think about these clearly before you apply them. Of course, this can be simplified slightly by multiplying by HO at both the numerator and the denominator, and this is what it works out to be. So VO is related to the input current II this way. Of course, what I want is VO by VI, but notice that VI, the input voltage, is simply the drop across HIII plus this voltage HRVO. So all I have to do is rewrite this whole thing with II being replaced by minus VO into 1 plus HORL divided by HFRL. And if we do that, it's a simple matter of algebra. Once again, it's best if you were to actually follow this along with pen and paper in your hand and do the algebra yourself. You get HR, which of course was already here, plus HI into minus the reciprocal of this. So minus HI into 1 plus HORL by HFRL. So VO by VI, that's our voltage gain. That after all is the most important quantity that we talk about when we talk about an amplifier. Although that's not the only important quantity, by the way. So VO by VI, this voltage gain, is simply the reciprocal of this quantity. And we can simplify this expression just by multiplying it out and so on. And it's a matter of simple algebra again to see that what comes out is minus HF into RL divided by HI plus this combination HOHI minus HRHF times RL. So this is a pretty complicated looking final result. Notice that the gain of the amplifier does not depend only on what is inside the amplifier, what is inside the black box, which of course decides what HO, HI, HR, HF are, but also on the load resistance. The more you load the output, the less the output voltage becomes. So this voltage gain expression is going to be very, very handy when we talk about general amplifiers later. Of course, there are other important quantities, as I said. You could find out the input impedance, for example, which is VI by II. and we have already done all the hard work here. We could find out the input impedance, and once again you would realize that the input impedance will end up depending on the load resistance. Notice that the two input impedances that we talked about, Zi and Hi, we have already talked about these two, but these were under different conditions at the output. So it's not surprising that in general the input impedance Vi by Ii will depend on the amount of resistance we have put across the load. These are all calculations we could do, and for example, also we could also talk about the fact that the output voltage decreases when the load resistance changes, or when the load resistance decreases so as to allow more current to flow. Essentially is a sign that there's an output admittance. The output is not just a controlled voltage source. Whatever input you give, a multiple of that is coming out at the output. You also have an effect due to an output impedance, which is causing the voltage to drop a bit the more current you draw. You can easily calculate that output impedance as well along these lines. We will do all that later when we talk of general amplifier theory. Right now I am just showing you what can be done. And at this stage, let me just point out one thing. Very often we will be using this circuit for analyzing transistors, and transistors in particular in the common emitter mode. You may not understand what that is right now. Don't worry, we will describe all that later. But in such situations, what often happens is HF and HI are substantial, but HO and HR are very, very tiny. If that happens, you get a much simpler expression, because this whole big thing down here just drops off and you end up with this approximate expression, minus HF into RL by HI, which ultimately is a very simple formula for the voltage gain of a transistor circuit. It is basically because of simplifications that occur like these approximations that we can do, and that are actually very good approximations. These are the reasons why for some circuits you prefer the H parameter equivalence, for some other circuits you prefer, say, the Z parameter equivalence, and so on. So the final result simplifies sometimes for one kind of parameters, not for the other kind. And that is the reason why we really have to spend time learning about all of them. Okay, fine. This was a rather serious application of the two-port equivalent networks. We will see much more of applications of this kind in later calculations, because they are going to form the bulk of the kind of calculations we do when we analyze amplifier circuits. The next topic I have in mind today is more for fun. It's something called the extra element theorem, or really a small part of the extra element theorem. And let me just tell you one thing about this. This theorem happens to be a rather important theorem in circuit analysis, and what makes it very surprising is that this is a rather recent addition to the armory of people who handle circuit analysis. Circuit analysis seems to be like something like a rather standard classical topic, and it's a surprise that something new can come about in recent decades. Most of the stuff that we have talked about, Kirchhoff's laws, Maxwell's method, Norton's method, these are centuries old. But this one, just a couple of decades. And it's still being explored, and people are learning more and more new results here and new applications. Of course, I'm not going to cover the whole of extra element theorem here. This, after all, is not really in our syllabus that way. But this is a very interesting application that I think everybody should know. At least one small part of it, which is the extra element theorem for finding effective resistances. And the reason why I'm discussing it here is that one way of deriving this theorem is by using a two-port equivalent network. So, what is the theorem? The theorem is something like this. Suppose I have a two-port network where I want to find the input impedance across effective input impedance across one pair of terminals. And there is one more thing out here, which is there's an extra resistance which you can connect across the output terminals. When I say extra, I don't mean it's not in the circuit. It is in the circuit, but for the purpose of analysis, we imagine that we have detached it, and later on we are going to put it back as the extra element. So we want to find out the effective impedance as a function of this extra resistance, Rn as a function of Re. So how do we do this? We will find later that there is a very nice final result, which is what the extra element theorem, at least for this particular case, tells you about. However, let's just proceed by using what we know, by using Z parameter equivalent circuits. You could of course do this analysis using the other equivalent circuits as well, and I would urge you to try at least one more so that you get more familiar with the usage of these equivalent circuits. But for the time being, I'm just showing you what happens when you put in the Z parameter equivalent in place of the black box there. Because you have Zi, Zr, Zo, Zf, these four parameters, you have this voltage source, the control voltage sources, and so on. So how much is the output current IO? Well, simple, is just the voltage Zf II divided by Zo plus Re, the resistance. And this is of course what makes replacement of the equations that we wrote down from Taylor series by equivalent circuits becomes so important. Just by looking at the equivalent circuit on the output side, you can immediately see it's a voltage source in series with the total resistance. So IO is simple. It's the voltage source divided by the total impedance with a minus sign. The minus sign once again because this voltage source is going to drive the current in this direction, and IO is flowing in the opposite direction. So a minus sign. Fine. But why do I need IO? Well, to find out the effective impedance between these ports, all I have to do is divide the input voltage Vi, the voltage between these two ports, by the current flowing in. But to figure out the input voltage, what I need to know is Zr IO, and that's where the IO comes in handy. So Vi, of course, is the drop across this Zi plus Zr IO. This is exactly what we have seen a while ago. But Zr is now minus Zf II by Zo plus Re. Just to compare this with the result that we had a while ago, when we were figuring out H parameter equivalence from the Z parameters of a circuit, we had shorted the output. That's why there Re was 0. Here Re is not 0. That's the only thing. But once you take this into account, we end up with this expression for Vi. And so the effective impedance, we are done. Rin Re is Zi minus Zr Zf by Zo plus Re. So if you knew all the Z parameters for a circuit, then fine. This is the expression that you would want to use. However, and this is very important, we would usually not know all the Z parameters for a circuit. Or it would be a lot of work to try to figure out all the Z parameters for a given circuit. It may be a much better idea to try to relate these Z parameters or this combination of Z parameters that we have here to certain easy to understand calculations or measurements that we can do on our circuit without bothering about what's going on inside. So let's look at this expression in some detail. Rin Re is Zi minus Zr Zf by Zo plus Re. Well, at least in our mind, we can switch the role of the input and the output. We can detach the extra element from the output terminal and ask, what is the equivalent resistance when looked in from the output terminal rather than from the input terminal? And that again is pretty straightforward. If instead of connecting Re across the output, I were to connect a resistance R across the input and looked at the resistance from the output side, which I'm going to call curly R as a function of R. Well, do we have to work it out again? The answer is no. All you have to do is realize that the Z parameter equivalent circuit is perfectly symmetric. So to go from the previous expression to this one, all you have to do is interchange the input and the output parameters. So Zi becomes Zo, Zo becomes Zi, and ZR, ZF gets interchanged. Of course, because you have ZR and ZF both here, that will not change much. So this is the expression for the effective resistance seen from the output terminals if we were to connect a resistance R across the input terminal. As I said, you didn't have to calculate this again. All you have to do is just realize that you can switch input and output parameters. Now, I will be interested in two particular special cases here. Which one is when capital R is 0, which is straightforward, is ZO minus ZR ZF by Zi, and the other is when capital R, the resistance that I'm connecting across the input, is infinity. That is, I'm opening out the thing. So the capital curly R at infinity is simply going to be ZO. Well, what is R in at infinity when you have an open output, and what is the input impedance? The answer is Zi. So, of course, ZO and Zi are just interchanges of each other once again. So these are the three special results that we need. Rin at infinity from this expression is just Zi. Curly R at infinity is simply ZO. Curly R with the input shorted is slightly more complicated, just this expression. So these are three quantities. One is I remove the extra element completely, I leave the output port open, I find the input impedance, that's Zi. I then find the impedance between the output terminals with the input left open, that's ZO. And when I repeat the same calculation with the output shorted, with the input shorted, I get ZO minus ZR ZF by Zi. So why is this at all useful? Well, let's look at Rin, Ri. You can of course see Zi, this quantity sitting here, can be taken out. So Rin, Ri, the original quantity that we wanted to calculate, is Zi into 1 minus this. Well, you can just multiply it out and you get Zi into Z. So just look at this. It's ZO plus Re minus ZR ZF by Zi in the numerator by ZO plus Re in the denominator. So this is what you get. But now notice what we have. The three quantities that we have up here, the three special impedances, the input in resistance that I measure with the output open or the extra element removed, is the factor sitting right in front here. The factor sitting along with Re here is nothing but the resistance which you see from the output terminal when the input is removed. And if the input is shorted, the resistance you see from the output terminal is actually this whole expression here. So finally we end up with this nice result. So this is the final result for the extra element theorem, that you can figure out the resistance, input resistance, a function of the extra element resistance if you know these three quantities. Rin infinity, curly R0 and curly R infinity. And another slightly different way of writing the same expression is this one. You just divide the numerator and denominator of the expression by Re and you write it in this form. Why is this form so nice and why do we want to talk about the thing in this form? Let me just explain this to you now. Now this form of the expression is what Middlebrook, the person who is behind the discovery of the extra element theorem, calls a low entropy expression. Now what does that mean? It means that instead of being a rather chaotic expression, jumble of expression with lots of circuit parameters, this is expressed in a rather neat form, which is easy to draw conclusions from. For example, if you knew that curly R with input shorted is very small compared to Re, I could easily simplify the numerator to be 1. A similar statement can be made about the denominator. So these expressions are easy to sort of express neatly and also draw simple conclusions from. So to illustrate this further, let me just show you how to use this extra element theorem for effective impedances for a very familiar calculations. Let's say we have our familiar old friend, the Wheatstone bridge, and what we want to do is find out the impedance of the Wheatstone bridge circuit as a function of this bridge resistance R5. So R5 here is our extra element Re. So we are trying to find out the input impedance of the circuit as a function of this R5. Just to point out once again, what are the quantities that we need to do this calculation? We need Rin infinity, which is just remove the extra element and find out the input impedance. We also need curly R0, which is short the input, put a short between the input terminals, and find the effective impedance from where the extra element was. So remove the extra element, R5 is no longer there, but these two terminals are still there. Find the impedance between these two terminals when the input is shorted. And curly R infinity, which is find the impedance between those two terminals again, but this time with an open circuit between the input terminals. Now all of these three are actually very easy to calculate for our Wheatstone bridge. What is Rin infinity? Well, you just remove the extra element. So R1 and R3 are in series, R2 and R4 are in series again, and the two are in parallel, and that's what Rin infinity is. R1 plus R3 parallel to R2 plus R4. Note that this in itself is a low entropy expression in the language of Middlebrook. Why? Because, for example, if I were to directly look at this and say R1 were much larger than R3, I could immediately see that this will be replaced by R1. If, say, I knew that R2 and R4 were both much smaller than R1 plus R3, then I don't even have to bother about this. I would know directly that the effective impedance will be nearly R2 plus R4. So all these simple limiting cases or approximations which you often have to make becomes very easy to make if you have expressions of this kind. Well, Rin infinity is just one of the three ingredients we need in our calculation. Is one. What about curly R0? You just put a short here. You want to find out what is the effective impedance. Of course, this puts R1 and R3 in parallel, because remember the short here simply means this line is joined. So R1 plus R3 is in R1 and R3 are in parallel, R2 and R4 are in parallel, and you have a series combination of them. So that's what curly R0 is. Curly R infinity, the last ingredient that you need, you just open this out. And if you open this out, of course, from the point of view of this extra element terminal or the bridge arm for our Wheatstone bridge, is R1 plus R2 parallel to with R3 plus R4. So these are the three expressions you have. Plug them back in our formula, and Rin R5 is simply this expression. I am not bothered to write down the whole expression here. It will just make it look unnecessarily complicated. But notice each of these three pieces which sit here are simple series parallel combinations. They are low entropy expressions. Their limiting cases are easy to figure out. Just as a final example, let us take a look at one more application. This is from the problem sheet that I had sent out. We had to figure out the current driven by this voltage source. Okay, and for that all you need really is the effective resistance between this and this terminal. Now there is no extra element in the circuit as it stands, but we can designate any one of the elements that we want as an extra element. So what we do now is designate 4 ohm resistance here as the extra element. So instead of 4 ohm, I've just put in a Re here. So that's the more general situation. I want Rin as a function of Re. And once again, this is the formula that we have. So can we calculate these three quantities? Let's try. Rin infinity is what we get as the impedance between these two terminals when I open this out. Of course, when I open this out, this circuit simply becomes a simple series parallel circuit. 7 and 8 ohms in series in parallel with the 5, 2 and 6 ohms in series in parallel with the 3, and the 2 added together. So that's the expression that you have. 15 parallel 5 plus 8 parallel 3. That's many ohms. Takes a calculator and a few seconds to figure out that this is 5.93 ohms. So that's R in infinity. What about curly R infinity? Curly R infinity is the resistance you see from this end. Remember, you have removed the extra element and you're looking in from the extra element side. And our curly R infinity is you have opened this out. Of course, this means is 7 and 5 in series parallel with 8, 3 and 6 in series parallel with 2, and so that's another pretty straightforward calculation. Once again, a calculator takes a few seconds to give you the answer, 6.44 ohms. What about curly R0? Well, you short this out. Now you should realize that what you end up here is the effective impedance of a circuit made out of this 8 ohm, 7 ohm, 2 ohm, 6 ohm on these four sides, and this 5 and 3 ohms in parallel. And just a moment's thought will show you that this is a Wheatstone bridge circuit again, an unbalanced Wheatstone bridge circuit with 5 ohms parallel with 3 ohms making up the bridge arm. However, we have figured out how to find out the answer for the Wheatstone bridge circuit just a while ago. So you can use that or any one of your favorite star delta transforms or other methods to find out the effective impedance of the Wheatstone bridge, and that gives you curly R0. So once you have found out curly R0, you can use it, plug it back into the formula and find out Rn for 4 ohms, which after all is the answer that we wanted. And once you know that, you've got your effective impedance of the circuit, divide 65 volts, the voltage of the battery, by that, and you've got the current, which was ultimately the question that was asked in the problem sheet. Now, the extra element theorem is not only about finding out effective impedances. There's just one aspect, one simple aspect of this. It's a very, very interesting topic. There's a book called Fast Analytical Methods in Electrical Circuit Analysis or something like that. I'm going to give a reference to the book in the website, which details the extra element theorem in its full glory for those of you who are interested. As I said again, it is exciting because in a subject which is as old or as classical as circuit analysis, it's rather nice to see a result which nobody thought of before, and is fast turning out to be quite an important technique. So in the next lecture, we are going to start talking about AC circuit analysis in some detail. Till then, bye.